Find the settlement from consolidation in inches from a load. In this problem, a load of 400 pounds per square feet is applied to a soil profile consisting of 6 feet of sand, 20 feet of clay, and 4 feet of gravel. We've also been given the pre-consolidation stress for the entire soil profile. Notice the groundwater table is at a depth of 4 feet. Consolidation will only occur in the clay layer because it is a fine-grained soil. Looking at our general consolidation settlement equation, we know the height of the clay layer is 20 feet, but we don't know which compression index to use, nor do we know the initial void ratio, nor do we know the initial and final vertical effective stresses. Let's first solve for the initial void ratio. From our equations, we know the total unit weight of a saturated soil can be determined from the specific gravity, void ratio, and unit weight of water. Solving for the void ratio and plugging in our known values, assuming the specific gravity of clay is 2.7, the initial void ratio computes to 1.23. Returning to our settlement equation, we can now plug in our void ratio. Next, we'll determine which compression index to use. To do so, let's first evaluate the initial and final vertical effective stress values at the midpoint of the clay layer. We add up the stress contribution from the unsaturated sand, the saturated sand, and from the top 10 feet of clay. The initial stress here is 999 pounds per square feet. After adding the load of 400 pounds per square feet, the final stress is 1,399 pounds per square feet. The pre-consolidation stress is greater than the initial stress, but less than the final stress, which means we'll use both consolidation indices. At this point, it would be efficient to derive an equation for the initial vertical effective stress in the clay layer as a function of depth. As before, we add up the contribution from the 6 feet of sand and from the clay, where we limit the depth d between 6 feet and 26 feet. After solving, the initial stress of the clay layer is 238 pounds per square feet plus d times 47.6 pounds per cubic feet. Now, let's zoom in on just the clay layer. We'll divide the clay layer into the segments which consolidate along the recompression curve only, the virgin compression curve only, and along both curves. The soil that only consolidates along the recompression curve has a final stress less than the pre-consolidation stress, and the soil that only consolidates along the virgin compression curve has an initial stress greater than the pre-consolidation stress. The remaining soil consolidates along both curves. The depth at which virgin compression begins occurs where the final stress equals the pre-consolidation stress. To determine this depth, we set the final stress equal to the pre-consolidation stress and solve. The final stress equals the initial stress plus the load. We can use our previously derived equation for the initial stress as a function of depth, and after plugging in our known values, we find d equals 11.81 feet. Next, the depth at which reconsolidation no longer occurs is where the initial stress is equal to the pre-consolidation stress. Again, we use our equation relating initial stress to depth and substitute and solve for D. Here, D equals 20.21 feet. Returning to our consolidation settlement equation, we realize we have to evaluate the settlement in 3 parts and cannot use 20 feet as our value for H. We compute the heights of each layer separately. Also, we recall the consolidation indices and use an average consolidation index value for the soil which consolidates along both curves. Lastly, we turn our attention to the initial and final effective stress values. We'll evaluate a point at the middle of each sublayer, determine the depth of each point, and compute the initial and final stress values, since we know the depths and we know the load. Finally, we can compute the settlement for each layer. For the top layer, we compute a settlement of 0.26 inches. This process is repeated for the middle layer and for the bottom layer. The total consolidation from the load is 3.13 inches. Returning to our possible solutions, the answer is B.